In the first video of this series, I talked about the geometric numbers. These are numbers which are not themselves real numbers, but they all square to real numbers. I promised that with those numbers, the bookkeeping of geometric transformations would become a lot easier. And in this video, I will deliver on that promise, just by multiplying them together. Let's consider the simple example of the two-dimensional plane to see how this happens. Ordinarily, we would write coordinates in 2D by first constructing an x and a y axis. And then if I had a point somewhere, for example over here, I would have to write its coordinate with its x coordinate a and its y coordinate b. And so we write this as a pair of numbers a, b. But now if I want to construct the distance of this point a, b to the origin O here, I would have to use the Pythagorean theorem. And what we do is I say r squared, the radius squared, is equal to a squared plus b squared. And therefore, the radius itself is the magnitude of r, is the square root of a squared plus b squared. But this means I have to do all of the work. I have to know the Pythagorean theorem in order to be able to calculate the radius of this point a, b to the origin. But wouldn't it be much nicer if I could just square the point a, b to automatically get a squared plus b squared? Well, this is possible, but we have to rethink how we write down coordinates. Instead of using real numbers, we should just be using geometric numbers. So what I will do now is use hyperbolic numbers to represent our axes. After all, real numbers square to positive real numbers, but so do hyperbolic numbers. So let's try that and see what happens. We take two different hyperbolic numbers, I will call them E1 and E2. Both of them square to plus 1, but they are not the same number. And now using those two new numbers, we can represent our coordinate a, b as a vector instead. So I write this as u equals a times E1 plus b times E2. And this vector should still square to a real number. This is called the contraction axiom, because the basis vectors that I used, E1 and E2, both square to real numbers. So any linear combination of them should still square to a real number, right? Because there was nothing special about the original choice that I made. So let's calculate u squared and see what this gives. So we have the vector u, which has a times E1 as its x component and b times E2 as its y component. So u squared is equal to a times E1 plus b times E2 multiplied by the same thing. Now I can first calculate a times E1 times a times E1, but remember, E1 squared is equal to plus 1. So this is simply a squared. And similarly, for b times E2 times b times E2, I get a b squared, and E2 squared is already 1. The cross terms are a bit more complicated. A times E1 times b times E2 will give me a, b, E1, E2. And the other cross term is b times E2 times a times E1. So that is BA times E2 E1. I have to be careful here not to swap the order of these geometric numbers, because I don't know yet if that is allowed, because these are new numbers to us after all. So firstly, we see that a squared plus b squared is nicely a real number, as we were hoping for. But this second bit is not. A times b, a and b are normal real numbers, so I can change the order. So what's left here is E1, E2 plus e2 e1. So in order for u squared in total to be a real number, this second bit here, e1 e2 plus e2 e1, has to be 0. And this means that e1 e2 should be equal to negative e2 e1. And we say that these numbers are therefore anti-commuting. So this is a very interesting property of the geometric numbers. They are anti-commuting. So with this, I do have the result I was looking for. Because what I now find is that u squared is equal to a squared plus b squared. But this is the result I was hoping to get, because if we now look at the original triangle, I had my side of A here and a side of B here, and this side I called U. And now we find that I nicely get that this side here is indeed a squared. This side here is b squared, and the diagonal is now perfectly u squared is equal to a squared plus b squared. So the Pythagorean theorem is now built into these numbers automatically, and now I can just take the square root of this to find the norm of u. So the norm of u is the square root of a squared plus b squared. So, in order to calculate the norm of such a geometric number is simply a matter of squaring it and then taking the square root again. So there's one interesting new number that appeared now spontaneously, and it's this e1 times e2. And I will actually give this a special new name, e12, and that is equal to the product of e1 and e2. What is the square of this thing? So I calculate e12 square, so that is e1 times e2 times e1 times e2. I just write it out. And now I use the anti-commutativity of e1 and e2 to swap the order of these two in the middle to get minus e1 times e1 times e2 times e2. And now you see that they are partnered up. The e1s touch the e1s and the e2s touch the e2s. And e1 square is 1 and e2 square is also plus 1. So the result here is minus 1. So I find that e12 squares to negative 1. It behaves like an imaginary number, but I obtained it just by multiplying together two hyperbolic numbers. Since it behaves like an imaginary number, I might as well go ahead and call it I for the duration of this video. What happens if I multiply our original vector u with I from the left? Let's consider this picture one more time. And now I will multiply u by the bivector I from the left. So the bivector was e1 times e2, acting on this a times e1 plus b times e2. So this e1 here, I would like it to be next to this e1, because then it squares away to give plus 1. But this e2 is in the middle. So to swap the order of this e2 and that e1, I pick up a minus sign because of the anti-commutation, and then the e1 squares away. So that will result in minus a times e2. On the second term here, this e2 is already next to that e2, so that immediately squares away to give me plus 1. And so I will be left with b times e1. So if I draw that into this picture now, the x-coordinate of this new vector is b. So that is roughly over here. And the y-coordinate of this new vector is minus a. So that's over here. So that means that this new vector has to point to this point here. So that's going to be this vector. I times u. So what we see here is that this is the original vector u rotated by 90 degrees. This is a 90-degree angle. And therefore, it is also clear what I need to do if I want to rotate by more than 90 degrees. I can multiply by any number of i's, n times, and that will give me a rotation of n times 90 degrees. But what if I don't want to multiply by multiples of 90 degrees, but instead want to multiply by something smaller or different? Well, I is the product of two vectors which make an angle of 90 degrees, and multiplying a vector by I rotates that vector by 90 degrees. So perhaps if we want to rotate by an arbitrary angle, we should multiply two vectors which make that angle instead. How do I rotate by any angle I want? I start with two vectors, the u that we had before, which is a times e1 plus b times e2, and a new vector v, which is c times e1 plus d times e2. So, for example, these could be a vector u in the plane and a vector v. Now I will compute their product, u, v. Firstly, a times e1 times c times e1 will just give me a times c, since e1 squares to plus 1. Similarly, b times e2 plus de2 will just give me b times d, since e2 squares to plus 1 as well. The cross terms are more interesting because a times e1 times d times e2 appears, and in the other term b e2 times c e1, I have to be careful with the ordering there, which is b c e2 e1. Now, this first part here is a real number, so we're done with that part. But in this second part, I can rearrange it slightly more aesthetically pleasing by reordering these two using the anticommutativity, and that gives me AD minus BC times the bivector E12. This first part here, these coefficients AC plus BD, you might recognize them as the dot product between two vectors. So this is the dot product between the vectors u and v. And this second term, we recognize this coefficient as the determinant of a 2 by 2 matrix or as the area of a parallelogram. And this term here in total, we call the exterior product of the two vectors, and it's written as u wedge v. And this might be a new product for you, a lesser known product. So let's explore what these two things really mean. First, the dot product, u dot v. So again, I start with my two vectors, u and v. And the dot product is proportional to the projection of the vector u onto the vector v. Now the projection of u onto v is the magnitude of u times the cosine of the angle here. So that gives me a cosine theta. Now there's one additional part, and that is it's proportional to that projection, and in fact it should be multiplied with the magnitude of the vector v. So I have to add that part in, and that is the definition of the dot product. The other one, u wedge v, again, I make a small drawing. Now the coefficient I already mentioned is actually that of the area of a parallelogram, and it is the parallelogram that u and v span together. And again, here I have the angle theta. And the area of a parallelogram can be calculated by the product of the base times the height. Now the height here is u times the sine of theta, right? In order to get that height. And again, the base is the magnitude of v. And I shouldn't forget that this is a bivector, so it is u multiplied by v. We can draw that this way as having a orientation. So I shouldn't forget to add here the bivector e12. The total product then of uv can be written as u dot v plus u wedge v. And if I plug in what we found so far, I find actually that this is the magnitude of u times the magnitude of v times the cosine of theta plus the sine of theta times this e12. But this you might recognize as Euler's formula, because this e12 is just the unit bivector which squares to -1. So I can actually rewrite this as e to the power I times theta. So for the last step, let's see what uv applied to u does, because that was our goal, right? We wanted to see if we could make rotations by angles different than 90 degrees. Now, what I will impose is that the magnitude of u and v are both 1 to make this calculation simpler now to do it graphically. So let's consider these two unit vectors, u and v. They have the same length and they intersect at an angle of theta. In a rotor, the product of u and v, the only thing that matters is the angle between the two. So I can just rotate this around, right? And it stays the same rotor. So in fact, what I can do is I can write equivalently the following product. I rotate v until it is at the position of u. And I call that v prime. And that means that u will have moved along, right? Because the angle here is still the same angle theta. So u prime is over here. So just to clarify, v prime is now the same as the original u. And now I can compute this product uv times u. Because the product is associative, so I can just place some brackets here. And the product uv, I can write that equivalently as u prime times v prime. But, as I said, v prime is the same vector as the original vector u. So this becomes u prime times u times another u, so that's u squared. And since these are now unit vectors with a length of just 1, this is actually just the vector u prime. So what has happened here is that if you recall, the original vector v was over here. So the vector v has just been reflected in the vector u to give u prime. So in fact, this formula uvu is a reflection formula. Any vector can therefore be reflected in any other vector by sandwiching it with that vector. And because the product is associative, we can also think of that as a rotor acting on a vector. Now this formula for reflecting is very compelling, because we can keep stacking it very easily and it's easy to see what will happen because the product is associative. So we can repeat this ad nauseum. And this is a very nice formula. And don't worry about it if you don't understand it at this point. You will see a lot of this formula in the rest of these videos because it's a very important one. Now, what we've seen is that just by considering the real plane using geometric numbers instead of real numbers, we can make a very compelling case for it, all right? And we can make a very compelling image of the real plane. For example, I don't have to remember the Pythagorean theorem anymore. We can rotate vectors by any angle, and we can reflect vectors in vectors very easily. But yeah, okay, I neglected to tell you some things. For example, if you see an ant on a table, does it appear to just be rotating on the spot, or can it also move across the table? So yeah, I neglected to tell you about translations, for example. In the next video, we will be doing just that, and I will show you how we can translate an ant across the table using rotations. So with that, thank you very much for your attention. I hope you enjoyed this video. Please consider subscribing to the channel and hitting that like button, and see you for the next video.